A viewer and patron, Richard Foy, said I should do a series on rocketry basics. At first I thought, what can I bring to the table that others haven't so far in terms of explaining how rocketry works? But then I realized I not only am an expert at 3D animation, I am actually teaching a course in 3D physics simulation using Autodesk's Maya right now, and this is a perfect vehicle, get it, for explaining how rockets work. In this first video, I'm going to explain what getting into orbit actually means and why it's a challenge. Later videos can discuss how rocket engines work, orbital mechanics, and perhaps more advanced topics like guidance and orbital rendezvous, all using 3D simulation to examine the intricacies of rocketry. Let's start with the easy stuff today, just getting into orbit. Hey y'all, it's Dr. Know-it-all. Today I'm going to start with an Isaac Newton / Jules Verne inspired rocket, a cannonball that gets shot into space. Of course, with the thick atmosphere on Earth, this is not workable at all, though it's actually been tried in the 1960s when they tried everything, apparently. The reason why it won't work is that speeds are very high through the thickest part of the atmosphere because you're shooting it out, so the maximum velocity is right at the start when the atmosphere is the thickest, which is the opposite of what you want. You want it to start slow and then get faster and faster as the atmosphere thins out. And of course, firing things out of a gun, the G-forces are far too high for a human being, and honestly for most cargo like electronics or anything like that to survive as well. But anyway, this is very instructive to kind of strip this down to the basics and look at it that way. As I teach tech animation and have written chapters of books concerning 3D simulation specifically, and I have a degree in physics as well, I feel I can at least explain the basics for those who are interested here. Again, what we're going to do today is extremely simplified, but we'll advance with subsequent episodes and eventually try to build a working rocket from the ground up. For today, we're just going to shoot cannonballs into space, and even that turns out to be a challenge. There is, of course, a reason saying something as rocket science is another way to say it's really, really hard. All right, so let's turn to Maya and have some fun. Alrighty, so this is Autodesk's Maya here. And you can see there's a bunch of stuff with the interface, but we're not going to worry about too much of that stuff. The only thing that really matters is our little planet that's here and our little cannonball that we're shooting off. Obviously, this is not to scale. This would be one heck of a giant cannonball. But actually, I guess we could consider this some sort of rocky asteroid. So maybe this is a Ceres or something like that instead. Anyway, so you can see what we've got here is a little cannonball that's set up on top. What I've done is I've set these both up as what's in Maya called rigid bodies. And basically what that means is that these things are physics simulated. So this is a passive rigid body, which means basically that it's got an infinite amount of mass compared to anything else. So it's not going to really react to anything. And then you can see that there is this active rigid body, which I'm calling the cannonball rocket because it's just a sphere. So we're going to imagine shooting this out of a cannon. If I put no initial velocity on this, you can see that it just falls to Earth. Or whatever, falls to the rocky asteroid. By the way, there's no atmosphere on this asteroid at this point. We will do that in a little bit, but anyway, so you can watch if you go close up and it just falls down. So that's your physics simulator, and actually if you let this run long enough, it would roll off the top. There is also one other really important point that's here is that we've got what's called a Newton field over here. A Newton field is a gravitational field, and if we look, it's dead center in the middle of the planet, which is, I guess appropriate. So anyway, in the middle of this planet is a Newton field, which is a gravitational field, but it's circular. So it uses the GMM over R squared, the Newtonian formula for gravitation, which means that as something gets around it, it will keep pulling it back, so we'll be able to get into orbit. It's not a flat gravitational field that pulls straight down. So anyway, the first thing we can do is we can do a little Blue Origin / Virgin Orbital, Virgin Galactic type of ride. So what we can do is we can give this, this is not exactly right. What I'm going to do is basically shoot it out of a cannon. We're going to give it an initial velocity in y, which is the straight up, and that initial velocity will immediately, gravity will start acting on it. So basically it's being shot up. There's no atmospheric drag. It's just going to go up and then gravity will pull it back down. So let's give it, something. These numbers are kind of arbitrary because obviously this is not set to scale at all. So don't worry about exactly what the numbers are, but basically what this means is we're going to go straight up and down. So off it goes, right into the land. So, okay. And if we increase this to like 50, we should have it go quite a bit higher, but it'll still come down. Yep. And wait for it. Oh my, it actually went up farther than I thought. There it goes. Okay. So the deal is that because the further up it gets, the less gravity affects it, which is what that formula GMM over R squared. The small mass is the mass of the cannonball. The big mass is the mass of the planet. The small mass is usually inconsequential. And then the radius squared means that the force of gravity goes down over the square as it gets further and further away. So obviously, if we look at this from a further distance, you'll see that what happens is the higher up that this thing gets, the less gravity affects it. So you can see it really keeps going. We can zoom out. And then it starts, and as it falls back down, it gets faster and faster because gravity gets higher and higher. So that's basically what's going on. All right, so let's see if we can shoot a cannonball into orbit here. We're going to only do this in 2 dimensions. There is a z dimension or a z dimension. You can see that the little thing over here. You can see the z-axis. But we are going to completely ignore that. We are only going to worry about x and y. So y is going up and x is going sideways. So we're going to attempt. So what we're going to do is I'm going to turn this velocity down a bit. Let's make it like 10. And then I'm going to give it some x velocity as well. So let's give it a little bit, like 10 and 10. So basically it'll shoot up at about a 45-degree angle here. And just like, you know, imagine a simplified cannonball. If you ever had a high school physics class, you've seen this before, right? This is your standard ballistic equation. And it goes up and it comes back down. But of course, we're on a round planet. So what if we keep increasing this? What if we double our x? Oh, it's getting further. And again, remember, we have no atmospheric drag. So this is what we're doing. Basically, we're going to keep on shooting this thing until we get to orbit. So let's increase this to like 30. Woohoo! There we go. It's getting closer, right? It's made it partway around the globe, around this thing. So I've played around with a lot of this stuff. My goodness, I've spent a lot of time working on this. But I've played around with a lot of these numbers, so I happen to know that an initial x value of 50 and a y value of 5 should get us into orbit. Let me back this off just a little bit so we can see better. It's going to be a terrible orbit, but it will get us into orbit, at least if the numbers work out correctly. And you can see that it slows as it gets to its apogee or apoapsis. Woo, come really, really close to the planet. But anyway, it slows as it gets further away, and it gets faster as it gets closer. And this is the way all orbital objects work. So that motion right there is Newtonian, Kepler, whatever, whoever you want to credit this with. But basically, that motion, as it gets further away, the apogee, well, at least for Earth, it's the apogee. For rocky planets, for any kind of planet, it would be the apoapsis. And then the perigee, or the periapsis, is the low point where it's moving the fastest. So anyway, you can see it's just kind of flying around, doing its thing. So the next thing we're going to try to do is we're going to add impulse. Right now what we did is we shot this out of a cannon, right? So this is just this is kind of a Jules Verne. Imagine doing this. He didn't really think about the atmosphere, but basically the idea is, I think it was Project Dart. I think it was Project Dart in the 60s where they actually tried to do this. They tried to shoot out a hypersonic missile from the dense atmosphere of the Earth, and they kind of sort of got it to work, but it was very, very complex and very inefficient. It's much better to use impulse, which is basically a rocket, which is going to have thrust over time instead of an initial takeoff. Oh, you can see it just recycled back to the beginning of the animation. But anyway, it'll keep going around in a really wonky, crazy orbit. We will fix all of that stuff in just a minute. All right, so now let's take a look at impulse. So what that means is, you can see there's impulse over here. We're going to treat this like a rocket ship now, in a very, very rudimentary sense. In other words, it's going to have power that is going to push it up and push it sideways. Now, I've already gone in here, and there's just a few keyframes at the beginning. If you actually care about this stuff, I can show you in the graph editor. All right, so what we've got here is there is an X impulse. There's actually a Y impulse also. I don't know why I didn't keyframe it on. But anyway, the X impulse starts, it gets up to a value of 2. Again, that value is completely unimportant. And then it turns off. So the rocket starts, the rocket goes, the rocket turns off. And there's also an impulse in Y as well to push it up off of the planet. So basically that's what happens here at the beginning. And if we look at, we can kind of zoom in here. It's a little difficult. Even with a small planet, it's hard to get the correct attitude. But anyway, if we kind of do this like one frame at a time, you can see it starts moving, goes up, and then it takes off. So you can see by frame 26 over here where we get to this other red thing, we've gotten to our last impulse. So after this point, after about frame 30, it's on its own and it's just flying in a Newtonian gravity field, right? So here we go. Again, we can, and again, this is a completely wonky, crazy orbit. But it does actually get to orbit, and it does its thing, and it comes really, really close to the planet as it comes back around the backside. But it does get to orbit, and it will fly around forever. But, of course, what we have not taken account of at all yet is drag, so or atmosphere. So in Maya, this is called drag field. I'm going to go ahead and turn this on. And I'm going to set a magnitude. Again, the numbers are absolutely unimportant. This is just to get this thing all set up. But okay, so we've got a very, very thick atmosphere all of a sudden. And this is not a realistic atmosphere because, of course, atmospheres are thick at the bottom and they wear off as they get higher. I'm not going to bother simulating all of that quite so carefully. What we really care about is the fact that, watch this thing now, right? It used to get to orbit, but now that we have a drag field, it's like, and that's it. Okay, so that's the atmosphere. And that's why we can't just kind of fire the thing up in the air. Now, on the moon, this would actually work, right? You could create a railgun or a cannon or something like that, and you could shoot your payload, right? If you were mining, I don't know, precious metals or mining helium-3 or something, you could put it in a container and use a cannon and shoot it up in the air, or use a railgun and shoot it off the ground. But atmosphere is a real nasty thing, and it causes lots and lots of problems. So you can see that our profile that worked perfectly fine before we had atmosphere doesn't work at all anymore. That little guy, that poor little guy, gets stuck. So we're going to have to do something different, and we're going to have to rearrange the flight path, which basically means we're going to have to go up first and then we're going to go sideways. So the deal is we have to get out of the atmosphere, and again, in real life, the atmosphere would be very thick at the bottom, and it would be much, much thinner than this on the Earth. It'd be just a tiny little hair, but I'm doing this for demonstration purposes. But so you could get up a little ways, and then you could start to turn sideways. But here what we're going to do is basically get out of the atmosphere and then go sideways and turn around. All right, so you can see here that I've altered the keyframes a little bit, and again, I'll show you the graph editor for anybody who actually cares. All right, so you can see that there is, from the beginning, from frame 1, there is an impulse in Y, which basically means that it's going up and up and up and up, and then it cuts off. So that part of the rocket engine, the imagined rocket engine, goes and it pushes up out of the atmosphere, and then the X thrust starts coming in. So if you imagined in real life, what would happen is the rocket would go up, and then it would turn sideways and start to hoof it sideways. And this is the reason why doing something like going up, like, you know, like what Blue Origin does or what Virgin Galactic does, is not nearly as difficult or energy intensive, because you don't need, notice that this sideways thrust lasts a really long time to get it up into the, well, to get it going fast enough, because otherwise, again, it would just go straight up and it would come back down again, even if it got out of the atmosphere. But most of the work that has to happen is actually the sideways work to get it around. So you can watch, it's going to go up and then turn sideways, right? There's a very violent correction that happens right there. So, you know, again, this is not, you wouldn't want to have that be quite so violent with an actual orbital rocket, but it's okay because we're just playing around with cannonballs right now. So there you go, and it gets into orbit nicely enough. So I'm going to rewind that and just push us just to kind of show the beginning of this process real quick. All right, so here you go. You can see we'll start off at frame 1, and as we go, it's got impulse, so it's pushing it up in Y, and then right around here, so as it gets close to the edge of the atmosphere, there you go. You can see that it actually starts to go sideways then, and that's the impulse in X. So that's the rocket taking off. Now we have no more impulse in Y, which means we're not pushing up anymore. We're only pushing sideways. That's all we care about. And off it goes, and then at that point we are now ballistic, right? We have no more impulse because we've cut it off. And so now from this point on, it's just flying via Newtonian mechanics, but it's out of the atmosphere, so all is good. Alrighty, so this is a slightly updated version of the file. You can see that there are more keyframes down here at the bottom, right? And what I've done is I'm going to circularize the orbit now. So what we did was we got up, but then we had just this wonky, crazy orbit, which was not at all circular. So basically what you have to do is when you get to the apogee, you have to do another burn, which basically causes it to circularize. It makes the well, it's much easier to demonstrate when watching. But anyway, so let's take a look at the graph editor again. So now what you can see is that we've got our original burn. This is what the initial one was, right? So we've got the Y burn, it goes up. Then we've got the X burn that starts. The Y burn stops, so it goes sideways. And then we're pushing sideways. And then when we get to the apogee, or apoapsis, we do a downward burn because we actually need to, the thing has gone around and it's now facing, you know, kind of downward, I guess. So basically it has to push down instead of up, but just, you know, again, it's pushing it down, but it's pushing it at the point that it gets the highest. And again, this will make a lot more sense when we actually watch this. So up it goes, off it goes. This is all the same as what it was before. And now, right as it got to the perigee right here, it gave it another little kick. And so what'll happen is, instead of making that crazy close call as it goes by, it'll now be, now again, this is not perfectly circular, but see how nicely that goes around and around. And so it's not perfectly circular. We would obviously have to be very refined about how to do this, but it's a much, much, much better orbit than what we had before. So there we go. And I'll back it up. Okay, so you can see it's going to come back to more or less where I burned that initial thing, right? So it's not perfect, but it's a pretty darn circular orbit. And again, I'm going to go back. So we're going to play the beginning part over. And now, okay, so now it's flying. So again, we're at frame 82 down here. You can see in the bottom. So it's flying. And as we get to right around here, which again is the apogee, apoapsis, that's kind of the furthest away point. That's the part where it takes the least amount of delta V. So what we're going to do is give it a little bit of a push, which is a delta V when it gets to that point. So it's moving away, it's moving away. If we don't give it that push, and again, I'm just kind of moving through one frame at a time. 23, here we go. Okay, so if we don't give it that push, it's going to fall back very rapidly and come really, really close to the planet again. But what we're going to do, and I don't know if you'll be able to see this kind of frame at a time, is now we're going to give it a little shove. And it really doesn't take that much. It's just a few frames of impulse. And you can see that what it's done is, as it's moving very slowly, it's easy to change its path overall, the orbital path. If it was moving very rapidly, the same thing would take a huge amount of impulse to actually do. Now, in a 3D animation, who cares, right? You can give it as much infinite impulse as you want, but in real life, you'd have to burn fuel to do that, which means you'd have to take more fuel into space, etc. So the best place to do this is when it hits that kind of slow-moving, faraway point. So again, just to watch this one more time, up it goes sideways, and then you can watch over here, we're getting close to frame 100, yep, and then a little push. And there it goes. And now it's circularized, more or less. You know, obviously it's not a perfect circle, but that's pretty much the way it works, which is why so often when you watch a SpaceX Falcon 9 launch, they will do a second engine burn. And it will be often really, really short. I mean, just a few seconds. It could be a minute or something, depending on what they're trying to do. If they're just trying to circularize the orbit, it's going to be very short. If they're trying to raise the orbit and get up higher, then it's going to be longer. Because, of course, you can add more impulse and you can make this orbit get bigger and bigger. Alrighty, and finally, we're going to add a... Got to select this guy. We're going to add a rotating planet, which means that this whole planet is going to rotate around. And I'm going to kind of, this is a pretty basic demonstration. You can see I actually had to get a little bit wonky with all the keyframes and everything. Again, if we look up here, this took a while, by the by, because it was complicated to actually get this, to get the rigid bodies to behave properly. Not that that matters at all, but basically you're going to see it at the beginning. It's going to do some wonky stuff, and essentially what I'm doing is holding it in place, and it's not happy about that until it's about time to launch. But essentially what we're going to see is that the rotation of the planet causes a huge amount of impulse already in terms of giving it that motion, which is why pretty much every rocket launches, well, sometimes they launch polar orbits because they need to do a different type of orbit, but if they're given their choice, right, they were going to launch from the west to the east because that's the direction that the planet is rotating, which gives it a huge amount of extra impulse, which means that you have to carry less fuel, etc. So here we go. You can see it's kind of bouncing around. Just ignore that stuff. And then the rocket takes off, and we get to give it a little extra juice. But you can see, even before it actually starts, as it goes out, it gets kind of thrown out, and it's already moving that way before the rocket really blasts off. So again, just ignore that part. Up it goes, and see how it's already rotating even without any extra force. And then basically what I did was I gave it those extra burns to circularize it. But because the planet is rotating, this thing has a lot of extra momentum. And again, it doesn't really matter in our fake world, but if we were in our real world where we had to carry fuel to do this, it would be a massive, massive savings to use the rotation of the planet. If we went opposite ways and tried to launch this thing backwards, we would actually lose a whole bunch of impulse. And so you would have to carry more fuel with it. So that's the reason, again, why if they're given a choice and they can use the orbit, they will go west to east. So for example, in Florida, they launch over the Atlantic Ocean from Florida, which means they're going towards the east. In Baikonur in Russia, they launch towards the east, also over the giant plains of Russia, etc., etc. So any place that they can do this, if they have to have a polar orbit, which is essentially going from, I think it's usually from north to south, but I think you can do it the opposite way. Anyway, it doesn't really matter that much. But that does not take advantage of this rotation because it's sideways to it. And so you actually have to carry more fuel in order to get into that particular orbit. As I'm sure you can see from even these simple simulations, getting into any kind of orbit is a challenge, even in a simple Earth model with a cannonball for a rocket. It gets way more complex when you have to actually build a rocket. Speaking of which, simulating how a rocket engine works will be the next video in this series. And by the way, this video I know is a bit of a departure from the usual for me, so I'm extremely interested in how you all like it. Basically, I'm going to continue this series based on interest, so if you want to see more of these, please like the video so I know you enjoyed it, comment about what you'd like to see, and definitely subscribe and hit the notification icon so that you will be alerted to the next one. Also, don't forget you can join our awesome Patreon community and help out the channel at the same time. The link is in the description for how to do that. Also, don't forget to check out our awesome and ever-growing merch store, and don't forget that we are both Tesla and Amazon affiliates. If you look in the description and you click on the links, you can help out the channel. Thank you so much. And as always, in the meantime, please feel free to ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.